At a high level, networking is the process of moving information from one endpoint to another across one or more intermediate devices. Those endpoints may be users, servers, sensors, virtual machines, or cloud-hosted applications. The intermediate devices may include switches, routers, firewalls, and service routers. The key idea is that communication is layered and cooperative. Applications generate data, hosts package it, networks transport it, and receiving systems reverse the process. Each device along the path does not need to understand the entire conversation. It only needs to understand the information relevant to its role. For example, a web browser sending a request to a website relies on the host operating system, the local network, one or more routers, and the remote server stack. That journey only works because each layer and each device contributes a specific function. To understand that clearly, we next examine the TCP/IP model. The TCP/IP model organizes communication into logical layers. The exact naming may vary across textbooks, but the functional idea remains consistent. At the top, the application layer includes user-facing protocols and services such as HTTP, DNS, and SSH. These protocols define what the communication means to the application. Below that is the transport layer, typically represented by TCP or UDP. This layer identifies conversations between applications and, in the case of TCP, provides features such as sequencing, acknowledgement, and reliability. UDP, by contrast, is simpler and does not guarantee delivery. Next is the Internet layer where IP operates. IP provides logical addressing and enables packets to move across different networks. Routers make forwarding decisions here by examining destination IP addresses. At the bottom is the network access layer, where technologies such as Ethernet and physical transmission mechanisms carry frames across specific links. A useful way to think about the model is this: applications create meaning, transport manages conversations, IP provides reachability, and link technologies move data across each hop. With the layers in mind, we can now explore how data is packaged as it moves downward through the stack. Encapsulation is the process of adding protocol information around data as it moves from an application down through the networking stack. Each layer adds its own header and sometimes a trailer to support the function it performs. The receiving side removes that information in reverse order through decapsulation. Imagine a user opening a website. The application creates an HTTP request. The transport layer adds a TCP header with source and destination port numbers. The IP layer adds source and destination IP addresses. Then the Ethernet layer adds source and destination MAC addresses for the local link. What began as application data becomes a frame suitable for transmission. This layering matters operationally. A router forwarding traffic does not care about the full application payload. It mainly acts on layer 3 information and then rewrites the layer 2 header for the next hop. Understanding encapsulation helps explain why different headers change at different points in the path. Next, we will make that more concrete by following a packet step by step. Let us follow a simple example. A laptop on network 192.168.10.0/24 wants to reach a server on 10.20.30.40 in another subnet. The laptop first recognizes that the destination is not local, so it must send the traffic to its default gateway. To do that, it needs the MAC address of the gateway interface, typically learned through ARP. The laptop then sends an Ethernet frame addressed to the gateway's MAC address. Inside that frame is an IP packet with the laptop's source IP and the server's destination IP. When the router receives the frame, it removes the layer 2 header, examines the destination IP address, performs a route lookup, selects an outgoing interface, and then builds a new layer 2 frame for the next hop. This process repeats at each routed hop. The layer 2 header changes hop by hop, but the layer 3 source and destination IP addresses generally remain the same end-to-end, aside from specific cases like NAT, which are outside our core scope here. At the destination network, the final router forwards the packet toward the server, and the server processes it up the stack. To understand why specific devices handle different parts of that process, we next look at network roles. Different devices play different roles in the network. Hosts are endpoints, They generate and consume traffic. A host may be a laptop, phone, server, or virtual machine. Switches primarily connect devices within the same local network segment and forward frames based on MAC addresses. Routers connect different IP networks and forward packets based on IP addresses. A switch does not usually make layer 3 forwarding decisions for ordinary Ethernet switching. Instead, it learns which MAC addresses exist on which ports and uses that information to deliver frames efficiently. A router, by contrast, is concerned with reachability between subnets. It maintains routing information and makes forwarding decisions based on IP destinations. Understanding these roles helps clarify how traffic moves through a structured network. Next, we compare local and routed delivery to see these devices in action. When two devices are in the same subnet, communication can occur through local delivery. In that case, the source host uses ARP to discover the destination host's MAC address and sends the frame directly on the local network. No router is needed because the destination is considered locally reachable. When the destination is in a different subnet, the host does something different. It still creates an IP packet for the final destination, but at layer 2 it sends the frame to the default gateway rather than directly to the remote host. That gateway, usually a router or layer 3 interface, becomes the next hop responsible for moving the packet off the local subnet. This distinction is one of the most important in networking. Many connectivity problems become easier to diagnose once you ask a simple question. Is the destination local, or does the traffic require routing? With that in mind, we can now consider the specific roles that control and forwarding functions play in a networked system. In any network, there is a difference between learning information and using that information to move traffic. Devices gather knowledge through configuration, protocol exchanges, interface states, and neighbor discovery. That information is then used to create forwarding behavior. For example, a router may learn that network 10.10.0.0/16 is reachable through a particular next hop. That learning might come from a static route, an IGP like OSPF, or another routing protocol. Once learned, the route influences the forwarding table so that actual packets destined for that network can be sent correctly. This distinction becomes especially important when we discuss service routers, because they separate high-level decision-making from high-speed packet forwarding. Before we enter that architecture, let us close the foundation section by summarizing the network roles in one integrated view. At this point, you should have a working mental model of network communication. Applications generate data. Transport protocols manage application conversations. IP provides addressing and routed reachability. Link layer technologies deliver frames across individual links. Hosts create and consume traffic, switches move frames locally, and routers forward packets between subnets. You should also recognize that each hop involves both continuity and change. The packet retains its end-to-end purpose and destination IP address, but link layer details are rewritten hop by hop. A host relies on a default gateway for remote destinations, and routers rely on routing knowledge to move traffic across the broader network. This foundation prepares us for the next topic: service router architecture. We will now move from generic networking principles into how a service router is built, how it thinks, and how operators interact with it.